Okay, so hello everyone. So this is an additional lecture on internet protocols, which I provide as a supplementary material for the mobile communications lecture in order to give you a better understanding how internet protocols are working. It's not part of the lecture in the sense that you would get questions during the oral exam, for instance, on this topic. But it's quite important to also understand in the following chapters in this lecture. If you want to read more on this topic, there are actually two very good books. One by Kurose, a top-down approach featuring the internet, which is really top-down, and the other book is by Andrew Tenenbaum, oldie but goodie. It's really a very, very old book. But an excellent book, very much focusing on computer networks and giving a good idea how different protocols or communication protocols between computers are working. There are two lectures at KIT that you could also visit if you're more interested in this topic. One is the Communication Systems and Protocols by Jürgen Becker and colleagues, but that more focusing on very specific applications. And then at the computer science department by Frau Zitterbart called Telematik, which is very much on internet protocols. Okay. To give a slow start, so what is actually a requirement on an internet protocol connecting two computers, possibly over a wide area network, so over the internet? So first of all, it has to be applied to various network configurations and environments, meaning it has to work using your mobile phone, it has to work in a local area network using Wi-Fi or an Ethernet cable. And every time you have different network configurations and different environments in the sense of with mobility, without mobility, and so forth. It needs to be scalable in a number of connected devices, so it has to work at home with just two computers connected to the network, but it also has to work, for instance, in a wide area network where you have millions of devices connected. It must be independent of hardware or operating systems, so it doesn't make much sense to have an internet protocol which would only work, for instance, with an Android phone or only with an iPhone, for instance. But you want to have an interconnectivity between different devices of different manufacturers, using different hardware and software. It must enable communication, in particular data transfer worldwide. So if you're here in Karlsruhe, you still want to access a server somewhere in the United States, for instance. It has to integrate between different devices, platforms, and networks that are interconnected. And you have to provide a common open, that's very important, an open framework for seamless networking, meaning that everyone must have a chance to access the implementation or the specification of these protocols. Otherwise, an integration or connectivity between different devices would be very close to only those who have access to the particular protocol implementation or specification. Now, there is the, I would say, rather famous OSI model, ISO OSI model. And the very basic idea of this ISO OSI model is that we divide our communication protocol into different layers. So if you take this example here, we have a system A on the left side and a system B on the right-hand side. And then you have some data that you generate up here, which goes then down through the different layers. And you have some communication down here, and then data runs through the different layers, again up until the data is consumed. Now, each of these layers has an own so-called peer-to-peer protocol with own states, with own messages and methods that are applied. And the main feature also of this layer model is that every layer can use different protocols. Take, for instance, this layer here. You could implement here very different protocols but they all are supposed to be compatible or usable with protocols used here on the lower layers. Okay, and the intention here is to increase the reuse of technologies. Yeah? So if we come later to this example, if you have on transport network layer, for instance, the need for a reliable transmission, you would use TCP. If you rather go for connectionless, low latency communication, you would rather use UDP. But both TCP and UDP would work underneath with an Ethernet stack, IP and Ethernet stack. So that's the main and basic idea. So you layer your communication protocol into different peer-to-peer protocols. Okay. Now, in the standard ISO-OSI layer model, we have overall 7 different layers. So that's the application layer, that's the uppermost one, the presentation layer, the session layer, transport layer, and then the network, data link, and physical layer. The physical, data link, and network layer are the only layers which are really concerned with the actual networking, networking of different devices, while the protocols up here are more logical protocols or logical layers that are there to organize your information transfer, so to implement certain characteristics in your information transfer. Now I have to. Yeah, okay. Within here in your communication part, so where we concerned with the network, we have so-called subnetworks. We come later to this point, what a subnetwork may be. And these subnetworks may even be hierarchical. So within a subnetwork, you may have other subnetworks. So now this ribbon up here, still there. Sorry, I lost my mouse pointer. So that. Okay, now we're back. Now, as mentioned before, you want to have an interconnectivity between these different layers and protocols applied on the different layers, such that, for instance, the transport protocol would have no particular information about the networking itself. That means you implement some network structure down here, let it be an wireless LAN, a mobile communication network, an Ethernet network, or based on optical fiber. Up here in the transport layer, it doesn't matter anymore. So the transport layer is completely transparent to the actual transmission technology that you use on the lower layers. An important thing, and we saw this all before in other lectures, is naming and in terminology. So on physical layer, we always talk about bits. So we transport bits on physical layer. On data link layer, we transport frames. And on the network layer, we transport packets. And this terminology is quite important in order to not confuse people. So if we talk about a frame, then we always talk about Ethernet. So on Ethernet, we transport frames, and frames are, for instance, switched, so forwarded using a switch. While on network layer, that would be the IP. And then we talk about packets, and packets are, for instance, routed compared to Ethernet frames. And this terminology is quite important. We also see this in the mobile communication lecture when we talk about the interconnectivity over the whole network. Okay. Now, how does this protocol is implemented? Assume you have, for instance, a website that you want to download. Then this website would consist here of some data that you want to retrieve to your computer. And then you put this to the application layer. And then the application layer adds an own header. That's this part here. And this this data that you exchange here on the application layer, this is then typically called a PDU, so a packet data unit, that is exchanged on one layer. And then this packet data unit is provided to the next layer, which takes this then as a so-called SDU, so a service data unit. It adds its own header that you see here. Then it puts this data, which consists of the original data plus the header of the previous layer. And then we have an exchange on the next layer. And then you go down through the different layers. And every layer adds an own header. And whatever your peer is on the other side will then perform certain actions and state transitions based on the information that is provided in this header. The only exceptions are the data link layer, where we often also have so-called tailing bits, which mark the end of a transmission. And that's quite important for the medium access, to know, okay, the transmission is now over. The next transmissions will start. And on physical layer, we then have just more bits that we put on the transmission medium, okay, like antenna or cable. Okay, now let's start through the different layers. So the first layer is the physical layer, and the physical layer is concerned with the actual physical transfer medium. That could be an optical fiber, copper cable, wireless medium. It takes care of modulating and demodulating the signals in order to enable the transmission. It performs channel encoding, decoding for error correction and detection and correction. Also part of the physical layer is the generation of the actual analog signal, so the digital to analog conversion. You perform synchronization of signals, which is very important in a network, that everyone is operating on the same time scale, and that you synchronize the transmission of different signals. And depending on the actual transmission medium, you have significant differences in reliability, data rate, latency, bandwidth. If you take, for instance, a mobile network, mobile communication system, you have a much lower reliability, for instance, compared to an optical fiber or an Ethernet cable. What is common to all of them is the border between the digital and analog signals. So this is always part of the physical layer, as well as the other functions like signal and encoding and then generation of the signal. The physical layer also deals with hardware components that are necessary to implement it. And eventually, provides the physical mean to transfer data between two network devices. Okay. Now, in this lecture, or actually the mobile communication lecture, we talk a lot about communication systems and networks, where it's important to connect multiple devices. And if we now network really on the physical layer, ignoring the upper layers, then we always come down to the broadcast channel. That means we have some data, and then this data is put on our transmission medium and then broadcasted to all these different receivers. And one example in a mobile communication system would be, for instance, an amplify and forward relay. So we have, for instance, up here a base station which transmits to your relay node. The relay node receives the signal and is amplifying it and then forwarding to all different terminals. And if we look on the protocol stack, we would go through the different layers down to the physical layer. Data comes in here. Then you go on the transmission medium, you go to the relay node on physical layer. Again, phi, so small. And then without touching the content of your packet, you forward it again on the physical layer to the destination, where you again have a physical layer. And then you go up all through the different layers. Obviously, that's a very simple implementation. Yeah, so because it's just forwarding on physical layer, you don't have to decode and re-encode and so forth. But it's also extremely inefficient. Yeah. Take one example. So there are still hubs. I'm not sure whether they're still used, but they're very cheap devices for Ethernet networks. Where I use one box here, so a so-called hub, Ethernet hub. And in an Ethernet hub, you forward every received packet on all ports. Yeah, so it's really, you don't look into the packet itself, you don't decode it, you just forward it to the other ports. And that means if you would have here our computer A, which wants to communicate with a server, and then it sends a packet to the hub and to the server, then the same packet is also forwarded to all other devices. Yeah. And in this way, it also occupies resources on communication links that are actually not concerned at all with this, with the communication between A and S. So you're occupying resources that are actually not necessary. In addition, it's also quite insecure because if the signal is repeated and then also delivered to the other nodes, it's very simple for the other nodes to eavesdrop your communication and try to decipher it and then get knowledge about what you're communicating. That's why typically networks are rather operating at least on layer 2, so on data link layer. And the data link layer is responsible for the access to the physical medium. Yeah? So the physical medium itself implements the translation of data into signals, and the data link layer takes care how the physical medium is accessed. Okay, it ensures reliable and error-free transmission. So, for instance, it performs CRC checks, making sure that there's to ensure the data integrity. It also divides data into different blocks. Yeah? For instance, if the data that has been provided for transmission is too large to be transmitted in one block, it would actually be segmented into smaller blocks, and then one frame after the other is transmitted, and at the receiver, they are then reassembled. It takes care of contention control, where here a good example is Wi-Fi, where you make sure that you do not have collisions on the physical medium. So this, for instance, CSMA CD or CSMA CA. It also acknowledges received data and informs the transmitter whether a retransmission is necessary. Yeah? So that's these typical ARQ process that you perform. Or in wireless networks, you often also have so-called hybrid ARQ. And this is used that if data was not successfully received, that you retransmit at least part of the data and then combine these transmissions at the receiver in order to eventually decode the data that has been transmitted. And that's extremely important for reliable connections. It also performs address management to make sure that data that is sent by a transmitter really is received by the intended receiver, yeah? So that data is forwarded to the correct devices. Also performs flow and congestion control. That's something that I'm going to talk later on, as well as sequence control, yeah? So that packets are delivered in order. Yeah? This can be done also on data link layer. Right. Now, how does this look in the OSI model? Yeah, so you would have some data here available in the network layer, and then you exchange basically here your PDUs, okay, between two network layer instances, and then you establish a data link connection, yeah, here with own PDUs, which include also the PDU from the upper layers. And you provide then these frames to the physical layer. Physical layer makes sure that it's delivered to the destination, and then it comes to the data link layer where it's decoded and then provided to the upper layer, so to the network layer. On data link layer, you would only see this logical connection here. So you would not see the actual physical connection. So you would not see whether it's a coax cable, an Ethernet cable, or Wi-Fi connection, but you only see that there is a data link connectivity between two nodes. And that's very, very important. So this level of abstraction, to avoid that we have dedicated data link layers for every possible physical implementation, because that would be quite a high complexity for the implementation. Okay. If we apply this now to existing networks, particularly our Ethernet networks, then the physical layer would map to the typical standard Ethernet, so 10 base, 100 base Ethernet, which is in fast Ethernet, or gigabit Ethernet, or I think even now 10 gigabit Ethernet. And this would be really our physical implementation, so the Ethernet cable that is used, or sometimes also then on optical fiber. And on data link layer in our networks, it's typically divided into a MAC, so medium access control, and a logical link control. The logical link control takes care of like multiplexing, flow control, frame loss detection. And as we see later, it is quite essential for bridging processes, while the medium access control can be specific for the actual underlying technology. So then, for instance, if you have a Wi-Fi, then you have a different medium access control. Yeah, in this case would be then CSMA, or with this RTS, CTS process that you are implementing. While in Ethernet, you then have a different medium access control. It also includes MAC addresses, frame or data encapsulation in frames, contention control, and so forth. Yeah. Maybe here to note for some of you that the maximum frame size in Ethernet, for instance, is 1,500 bytes. And if you then have IP packets which are larger, or data that you want to transmit that is larger, you always have to fit it into this 1,500 bytes. Yeah? So you have then to perform this segmentation and reassembly that I mentioned before. Now more on the specific, let's say, responsibilities of the different layers. So the logical link control takes care of connection control. So it manages the establishment, maintenance, and termination of logical connections between devices, and then provides a mechanism for initiating, for coordinating, and releasing data transfer sessions. Then you have the flow control, which helps to regulate the flow of data between devices and making sure that the receiver can handle the amount of data that is, or the speed, how the data is provided to the receiver. You have error control. The LSC detects and manages errors and handles also the error correction, for instance, with retransmissions. We have framing, that's what I mentioned before, and also addressing. Yeah, so it also includes on addressing information. Then we have the MAC. So one example would be for Ethernet. The MAC is defined in 802.3, and it controls the access to the shared network medium. Yeah, so allowing multiple devices to access this medium. It manages contention and collision avoidance. It performs also frame encapsulation for the access to the medium itself, addressing and data framing. Okay. If you now look again on how we network these devices, then take for instance here the left side. Oops. Oh, my computer doesn't want to. Okay. Here, and this is an Ethernet network. Yeah, so I have a switch there. And then you have again terminal A, which wants to, or let's start here, yeah, which wants to connect. Okay, so my computer is now a bit doesn't want to work right now. Okay. Then you have here this terminal A, and A wants to communicate here with S. So, and as in the example before, A would now send a message and includes the address of S. Then you would come here to this device, which would be a bridge, or switch in this case, and it would see, aha, okay, this frame is intended for S. S is connected here on this port and then forwards the packet. That means in this case here, if you operate on data link layer, this particular frame is not forwarded to the other ports. Yeah, in this way, it is operating much more efficient, yeah, because we are not multiplying the data to connections where the data is not supposed to be transmitted. And it's more secure, yeah, because eavesdropping becomes much more difficult. The question now is, what would, or how would you implement this if A wants, which is here, in this case, connected to a wireless LAN router or switch, and if A wants to communicate with S, yeah? Or let's start with this example, that if A wants to communicate with D, then A would send also here the frame to the Wi-Fi bridge. It would see, aha, okay, D is connected actually to my network, and then again also forwards only to D. But in the case that A wants now to here communicate with S with one packet, the question is, how does now the packet comes from here, from this VLAN bridge over here to this switch, and then further to the server S. And that's exactly where bridging comes in. And by the way, sometimes these Wi-Fi bridges are also called translation bridges because they translate from a Wi-Fi system to a fixed line Ethernet LAN, for instance. And the way how this bridging is done and to get data, for instance, in this case from Wi-Fi to an Ethernet, is defined here in the IEEE 802.1 standard. And this 802.1 standard is probably one of the most important IEEE standards because it defines very well how we forward on layer 2 frames in networks, also between different technologies, also taking quality of service into account and so forth. And the bridge itself operates transparently. So when you have, for instance, here a Wi-Fi device, which is trying to access a fixed line or a server which is connected through a fixed line connection, then this would not be visible to the device connected to the Wi-Fi network. Yeah? So it would be completely transparent to it because of the bridging process taking place in the bridge. Now, how does this work? You would typically have here your frame that you send. You have again an own LLC connection, yeah, through these devices. And then you have an own MAC connection within Wi-Fi. Yeah, so that's in this case 802.11. You transmit the data within your Wi-Fi device. It comes to the bridge, and then you have here this bridging process, which I come to on the next slide. Knowing, okay, this frame is now intended to for this network part, so subnetwork, and then forwards the data to, in this case, Ethernet MAC, so 802.3, where you again have an own connection between these two devices. Okay. Yeah. Okay. Now, one of the probably now most important questions is how does the frame find its way through the network? And this is done using the so-called forwarding table defined in 802. So I write it down here again. So IEEE 802.1. And a forwarding table is basically some sort of lookup table think my pen runs out of power. Okay. So it's some sort of lookup table, and in this lookup table, it's written down which device is connected on which port. Okay. And in order to fill this table, what is done is take again this example that A wants to communicate with S. Then A would get data intended for S. Okay. And then A doesn't know where S is actually located. So it would send a request, a broadcast message, where is S located? Okay. Then this question, so to say, is then forwarded on each port. Yeah. So the frame here, the bridge here, we actually take the packet that was transmitted as broadcast, send it all the way here, then this bridge receives it and sends it also on all different ports. And eventually the frame will be received by S, and then S will respond with a message saying, that's me, yeah? And would inform the bridge, I'm S. Okay, so my pen is now working, good, okay. Okay, and the good thing is now, and by the okay, it wants to tell A, yeah, that this is S. The good thing is now when this packet here, so the question for S was received by the bridge, it actually learned, okay, A is connected to port 1. Yeah, so it will write down port 1. I have the MAC address of device A. And when S is responding and saying, hey, I'm S, please tell node A, then the bridge can also write down, okay, on port 3, MAC address of device S is connected. And this way also knows, okay, if this comes in and is intended for A, okay, A is connected to port 1, and then it goes all the way back to A. And once A knows, that's where S is connected, then it can actually send the data to S. And the same would then actually also happen for the other devices. Yeah, so you would maintain a forwarding table saying, okay, on port 1, for instance, you also have MAC address B connected and MAC address C, and on 2 MAC address D. Yeah, and this forwarding table is then maintained by the bridge. Every once in a while, this table is also updated. And the reason is that due to mobility, yeah, for instance, if you are on a Wi-Fi network and then you switch the access points, or if you just unplug your computer and plug it in to a different computer, the location of your device may change over time. Okay. If you want to see this actually really working, well, how this works in the network, I can just recommend you to run on your Linux PC TCP dump. Yeah, and then you see so-called ARP messages, or this address resolution protocol messages, and there then you see how the device is actually asking for different MAC address, or actually IP addresses, and then the corresponding MAC address is delivered. Now, the problem in this method is scalability, yeah, because obviously the complexity increases with an increasing number of terminals. Yeah, just imagine if a whole KIT would be one data link layer network, then one bridge would have to maintain all the different MAC addresses across the whole KIT domain, which, I don't know, probably tens of thousands. And this doesn't really work. So you have to take measures to avoid that one bridge has to maintain MAC addresses for such a large network. Dynamic network changes. So if the network now changes because of, for instance, mobility, you would have to handle this in real time. Yeah, so because you cannot wait 10 minutes until such an update is done. And this is one of the reasons why, for instance, your computer is sending probably every 30 seconds or so ARP messages to inform the network, hey, that's my computer, that's me, just to give you an update. Also, topology changes within a network when links are added or removed, and in this way also the paths within the network are changing. Quality of service, because the forwarding at those bridges needs also to incorporate quality of service, and for this there is the IEEE 802.1q standard. Yeah, that's the famous VLAN standard, where so-called priority code points are defined that are basically different queues that are defined within a bridge, and then each queue has a different priority. And security considerations, yeah, because you have to protect the integrity and security of the forwarding table. That's probably one of the possibilities to attack a network, and then you just perform MAC spoofing by overloading this forwarding table. Okay, now the next question that we would have to ask ourselves is if A wants to connect to S, but it actually doesn't have the MAC address of S in the data link layer, what is the address or the name with which A is asking for S, right? And this is done on network layer. Yeah. So the network layer is responsible for reliable transmission across a network, yeah, not only a subnetwork, but really a network. It's the highest layer responsible for the actual end-to-end transmission within our network. It's aware of topology, yeah, in order to route and packets through my network. Yeah, if we have, for instance, a tree topology or ring topology, and this is reflected on network layer in order to find optimal routes through the network. It performs congestion control. And I think that's, from my point of view, the most important functionality and task is this internetworking. Yeah? So it makes sure that you can connect different subnetworks or different networks with each other. Okay. It also performs fragmentation, reassembly, sequence numbering, flow and error control. And towards the data link layer, it always has to indicate the data link layer connection that is used, which eventually also maps to a physical link. Yeah? That's, yeah, genau. So how does this look again on the ISO-OSI model? Pretty much as before, yeah, you would get some PDU up here from the transport layer provided to the network layer, which establishes an own logical connection, and then you pass the data through the different layers. And again, the network layer itself is actually transparent to the data link layer and physical layer that is used underneath. And a good example is the mobile communication network. For instance, the 5G, which is not using Ethernet. Yeah? So compared to a Wi-Fi network or a fixed line network where Ethernet is used, on top of both, you can establish the same network layer connection. So in this case, an IP connection. Okay, now in terms of standards, you have, again, as before, we have here the logical link control and MAC, which build up the layer 2. We have down here also physical layer. And then layer 3 is then the IP protocol, which takes care of addressing. Yeah, so every device has a unique IP address. And this is then used to identify source and destination. It takes care of fragmentation, reassembly, routing. Yeah. Okay, now how does, again, the networking look like? Take, as before, our example, we have here our node A. And A wants to connect now, in this case, with D. Yeah, so we have here a data packet, A to D. Then the process that would take place is the one that we had before. Yeah, so you could actually easily connect here on layer 2 within this network. But what happens if A wants to connect instead here with the server H? Yeah, so I have now a second packet A to H. Then this computer up here is actually in a different subnetwork, and you somehow would have to get the data across this router here. So this is now our router to the other subnetwork. And for this, we have so-called subnetworks or subnetwork masks, meaning, take here, so we have here a subnetwork 192.168.1.0/24, and this /24 represents subnetwork mask 255.255.255.0. And if A now knows the target address H, what it would do, it takes the IP address of H and does a binary AND with the subnetwork mask. Okay. And if the result is not then the own subnetwork, yeah, in this case, this one here, then A would know, okay, this target computer is not located in my own network, yeah, but it's located in a different network. And for those cases, every computer has a so-called routing destination, and so you can actually retrieve this on your computer using route. Yeah? So if you enter route on the console, then you would see this. And it would look on, okay, do you have a predefined route that I have to take in order to deliver my data to server H? Typically, you also have a so-called default gateway, default route. And this default route is then identified here with your gateway router. Yeah? That means A learns if you want to provide or if you want to deliver this packet to H, you first have to provide it to your gateway router. Okay. That means A would send the packet to the gateway router, so this path here, and this gateway router would look into the destination address and see, aha, it's actually intended for server H, and then forwards the packet here to server H. And the address of server H is known to the router because of the same process that I explained before, yeah, using address resolution. Yeah, so this one has an IP address, and then with ARP, it's permanently informing the network, hey, that's me, that's my IP address. I have the following MAC address. Okay, then this MAC address is stored. MAC address is then also stored here in the route in this gateway, and once it's receiving a packet for H, it will then deliver it on the corresponding port towards the server. Yeah, okay. Now the question, now again, the question is, how is this IP address maintained, yeah, in this end-to-end connection? What is now also the difference into this data link layer connectivity, which is illustrated here on this figure? If you take again, so this would be our source that we had before, A, and this would be in the server where I want to deliver my IP packet. Then the packet would start here on a network layer, and it goes all the way through data link physical layer, then on the physical medium, and then up here again on the network layer in the router. And the router, if it's really just a router, it would not change the IP packet itself. Yeah, it will just forward it on towards the correct subnetwork where it has to be delivered. And then it goes again down to the data link physical layer and to the destination. On data link layer, you would maintain individual logical connections. Yeah. That means a router will change the source and destination address within the frame. Yeah. So because you have here your frame, yeah, your PDUs, where a certain source A is defined and the destination is then B in this case. While in this PDU, your source would be the router B and the destination would be then the server C in this case. The IP packet itself is not changed. Yeah? So the IP packet so there will be one logical IP connection between source A and the destination C. And this is this importance of IP and layer 3 networking, that you can connect different subnetworks, for instance, using Ethernet in a very transparent way, and that you can route your IP packet through these different subnetworks. Okay. So if you're actually interested, you can always see this process also on your computer. If you use, for instance, route, that will deliver you the different routes that are defined on your computer. You can also use IP tables. And IP tables will actually tell you whether there are any specific routing rules defined. Yeah? So in general, that's important for firewalls. Okay. Now, one important concept that I would like to mention here is again also is the so-called NAT, so network address translation, so NAT. And NAT is actually something used because if you now take this amount of IP addresses, yeah, so if you have many subnetworks and all of these subnetworks define their IP space, then at some point in time, these IP addresses are exhausted, right? So there are no IP addresses left to define new subnetworks. And that's why we have typically these 192.168 are actually IP addresses for local areas. And then at this router here, you also translate your local IP address into a public IP address. And then you would also change here the content of the packet and not anymore say that it's a packet from A to C, but you would say it's a packet from B to C. Yeah, you then basically have one connection from the router to a destination server, and behind can be many different local area connections. And this router has to take care that these many different local connections are mapped then to these public connections. Yeah, in this case, then from B to C. This has the advantage that you have here in this direction, you have one public IP address, yeah, that is known, for instance, to the internet, while in your subnetwork you have private IP addresses. And then you can reuse these private IP addresses for each subnetwork that you define. That's the advantage. The disadvantage is, whether it's a disadvantage. So what now happens is the actual IP address of the source is now hidden to the destination. So the destination will always only see the router as the source of a transmission, and it will not see where it originally came from. Yeah? And it's actually very good because this allows you to hide your nodes within your subnetwork and to avoid that this private information is made public. On the other hand, it also means you will never be able to directly reach as your private terminal here on the left side from the destination. So you will never be able to establish a connection from the destination towards the source because the destination doesn't have any information about the source. Yeah. And that's this network address translation, which is used in all enterprises, also in mobile communication systems, also KIT. Also KIT will have some public IP addresses, and all the IP addresses that we are using here in our KIT network, There are private IP addresses which are not made public to the outer world, which is good. Yeah, so that this also avoids that someone from the internet would be able to access your computer directly and start hacking it. Okay, now as mentioned before, so on network layer we have sometimes a very complex topology interconnecting different routers. So sometimes there are many different ways, paths that an IP packet can go through your network. And for this, you need different routing strategies. One is fixed routing. Yeah, so they have an individual route for each source destination pair. That's, for instance, when you have default gateways. Yeah? So you have a fixed route saying, okay, for these and that. So if nothing else fits, then use this fixed route towards the default gateway. Okay, that's also default routing. Flooding, so you just flood the whole network, which is obviously quite inefficient and non-adaptive. Random routing and adaptive routing. Yeah? So in adaptive routing, you would, as the load of the network changes, you would also adopt your routes. And here the probably most well-known protocol is the open shortest path first, so OSPF, which I think is the probably most often used protocols in routers. Okay, so these were now the three networking layers, so the physical layer, the data link layer, and the network layer. So we have PHY, yeah, our physical transmission, then Ethernet on top, for instance, and then IP on top. And on top of this, we have the transport layer. And the transport layer is now responsible for the data transfer between computer processes or applications using so-called ports. Yeah, because now imagine if you would not have the transport layer and only an IP connection, and now you get some data, it would be very difficult for your computer to identify which of the applications running on your computer, like a web browser, your email program, is actually responsible for processing the data that has been just provided. Yeah, and for this we have so-called ports. Yeah, so every IP address you can then assign so-called ports where data can flow in and flow out. Yeah, it's responsible also for data segmentation, reassembly again. It ensures reliable delivery, or can. And I would say the probably most important task is this reliable connection setup and ramp down. So it's responsible for setting up a connection between two computers and then maintaining this connection, so making sure that the connection is still existing, and then also perform a graceful ramp down to make sure that really the connection is closed and all the data related to this connection has been delivered. They are connection-oriented and connection-less services. So that's the difference between TCP and UDP. So in TCP, you have an active connection that is stateful, while in UDP, you're connection-less. Yeah? You just transmit the data to the computer without actually knowing whether it was received or not. And TCP is also crucial, yeah, for opening connections through a NAT. Yeah, so what I explained before, because only through these ports you can actually identify the different connections that have been triggered by devices in your subnetwork, allowing for mapping traffic that comes in from the internet back to the connections that you have in your local subnetworks. Okay, this is again the OC layer model, just to map it. So we have, again, physical layer, data link, network layer, and then here on transport layer, probably two most important and most often used protocols are TCP and UDP. So the difference between TCP, UDP, so TCP is connection-oriented, while UDP is connection-less. In TCP, we have a guaranteed delivery, while in UDP, you have no recovery mechanisms defined. The ordering in TCP is guaranteed, so it has sequence numbers and makes sure that the data is delivered in order towards the application, and in UDP not. TCP has a flow and congestion control. As mentioned, I'll come to this later. TCP has significantly more overhead in order to maintain the state and maintain the reliability on the connection. And in this also has a higher latency. So that's why for time-sensitive applications, you would rather use UDP than TCP. And you have no integrity. Or actually, this should be here. So you have actually no guarantees on integrity for UDP, and which has to be provided over the top. Okay. Now again on this idea with ports, to illustrate this, if you again connect your computer here with, for instance, you come up from here with some website request that's typically HTTP, which typically uses port 80. Yeah, so then you would say, okay, I want to access destination C on port 80. Yeah, and then you create your data packet here, you add your header with this information that you want to access destination C on port 80. Then you go on to network layer. Network layer would see, aha, okay, I want to access a certain IP address corresponding to destination C, and says, okay, I want to build here, shown, a packet from IP address A to IP address C. Then this is delivered to the Ethernet layer, where you then say, okay, where does IP address C, where it's located? And it will see, okay, I have to actually go first through router B, and then builds an Ethernet frame with the destination address B of the router. Then you go on physical layer, you provide it to the router, and then the router will see, aha, this frame was indeed intended for me. It will decode it, see, aha, it's then IP address C where it has to be delivered, and puts it on the right network interface card. It builds again a new frame with destination C, so destination MAC address of C, provides it to C, then it goes up here, and then eventually the transport layer will see, aha, yeah, here it's intended for port 80, and then this data will properly provided then to HTTP in order to process this HTTP request. So these ports are extremely important and there are actually quite many predefined applications that I also list later. So we have HTTP on port 80, SSH on port 22, and they are worldwide defined, which is very important if this guy here has, for instance, a NAT process, and a firewall. Yeah, in those cases, it's very important to also stick to these port numbers, because typically you have them predefined firewall rules, for instance, for HTTP traffic on port 80. Now let's come to congestion and flow control. So congestion control relates to the network state, meaning if I have a network, or if I have a process here which delivers data with a certain data rate, okay, and you send this to the network, and the network has a bottleneck, then this eventually will lead to some buffer overflow on your routers, and then packets are dropped, and this needs to be avoided. And first it needs to be avoided, and if it happens, it then actually has to be detected and migrated. And this is this congestion control mechanism. So the congestion control is to avoid that we have an overload in our network. And the second one is the so-called flow control. And the flow control actually relates to the source destination link. And typically, how fast can my receiver really process the data? So if we have, for instance, here a device that is not capable of digesting and then processing the data in the speed that it has been provided here by the source, then you would actually have to control the inflow to the network. That's where the name comes from. And for this, you typically have some stop and wait or sliding window protocols. Stop and wait typically rather on data link layer, and in sliding window then rather on layer 4, so TCP. Now, the basic assumption of the congestion control is that there are no errors on the connection itself. And here now come into this problem that in a wireless network, we do have errors on our wireless link. Yeah? So in an Ethernet network, typically you don't have errors on the link itself. So very rare events where we have an error event on the network link itself. So the congestion control is there really handling buffer overflows at routers. Yeah? If the data rate on the link itself is just not sufficiently high in order to transport the data that has been provided to the router. In wireless link, that's different. Yeah? So for instance, a mobile network is operated at a firmware rate of 10 to the power of so between 1 and 10%. And you quite often drop packets. And then this is actually not necessarily an overload of the network. It's rather because that's an optimal operating point in our mobile network. But it would still potentially trigger the congestion control, yeah, which in this case wouldn't make sense. And that's why TCP over a wireless link is quite challenging, yeah, because you have, due to this packet drops, you very often go into the reduced data rate of your TCP link, yeah, which is trying to avoid a congestion. Which, by the way, is something that you can very nicely also see if you use, for instance, Wireshark at home, and then run a wireless LAN connection, and then you will see that because of this TCP link, you quite often have a data rate drop, or use, for instance, iPerf. So that's another possibility where you can test it if you use iPerf, and once with UDP and then with TCP. And you will see that the data throughput with UDP is significantly higher compared to TCP. Now, how this congestion control is working is, if you take here this figure, that's time, and that's the so-called window size. And window size refers, that's this CWND, contention window. Congestion window, yeah, congestion window. And this window is sort of the amount of data that you can transmit. Yeah, so the larger the window, the more data you actually are transmitting until you wait for an acknowledgement. Then how TCP works is you have a so-called slow start. You go up here, and then once you cross a certain threshold, you go in the so-called congestion avoidance phase, which is this linear one here. So that's the so-called congestion avoidance. And then at some point you run into a packet drop, yeah, and where you just miss the acknowledgement from the destination. And then you go down as you reduce the window size. That means you lower your rate with which you put data on your link, and you go in the so-called fast recovery. Yeah, so you go then it's the fast recovery until you again have a packet drop or even a timeout, and then you would go down again to window size 0. Yeah, this would actually happen when you have a timeout, meaning when you do not hear anything from the destination, and then you start again with your slow start, congestion avoidance, and so forth. And that's the very typical shape how a TCP connection looks like. Yeah, and as mentioned, use Wireshark. And for instance, Iperf, perform a link test with Iperf, and you will see exactly this shape of your data throughput. And this is what is very challenging for a mobile network, which would work pretty well if you have a very constant rate with which you transmit data. But this permanent variation of your data rate is quite challenging, because then you have to react very fast with your scheduler to these changes. Yeah, you cannot pre-reserve any resources because you never know how much data is resources are requested with the next transmission. Okay. Now, on top of TCP, we have many other protocols. One important one is Ioip. So it's not on top of, not on top of TCP, it's actually on top of IP. Or it's actually to resolve IP addresses. So it's a layer 3 protocol in this case. And how it works is your source node is actually sending a so-called ARP request. Yeah, it's broadcasted, in which it asks for an IP address and the corresponding MAC address. Yeah? Then at some point it's received by the destination, which is then responding in unicast with its MAC address, saying that's my MAC address associated with this IP address. It supports these dynamic updates. So typically you have very periodic ARP messages. I think typically every 30 seconds you're transmitting them. And it's therefore conflict detection, yeah, particularly when you have DHCP in your network. So dynamic IP address assignment, ARP helps you to resolve those conflicts and trigger a reassignment of IP addresses. There it's the method, yeah, that is state-of-the-art method used in Ethernet network and very essential if you're using DHCP. DHCP is the dynamic host configuration protocol that probably many of you are using. The first one is so what it's used for is discovery. Yeah? So that means your device broadcasts a discovery message to a server, yeah, before it has an IP address. Yeah? So this again a layer 3 protocol. And it tries to discover whether there is any DHCP server within the network. The server will eventually receive it and in unicast respond to this request to offer an IP address plus additional information. So then the subnet mask, the default gateway, DNS server, and so forth are included in this response. Then the device will request the IP address and notify of the actual configuration that has been chosen. And then the server will actually acknowledge that. So it will then confirm the configuration and provide possibly then also additional information. If you're here connected at KIT, then KIT also uses DHCP because it would be the alternative would be to assign every node a static IP address, which would not scale, because there are way too many devices here at KIT. So whenever you connect to, for instance, to the Wi-Fi network, then you first connect with a DHCP server, and the DHCP will then provide you an IP address. It's also used in mobile networks. So mobile networks also have a DHCP process, or when you, for instance, go to guest networks, so like eduroam and so forth, then DHCP is quite essential. And last but not least, ICMP, so the IP control message protocol, also on layer 3. Probably where you will know it from is ping, so echo request reply, which is essential for reachability analysis. So if you want to know that a certain server is reachable and available for you, you would always use ping. So you send an echo request to a particular IP address, and then you wait for the response. It's also used for network tracing, so trace route, in order to see what is the path that your packet has taken through the different network elements, and also to determine the maximum transmission unit is quite important. If you have different subnetworks with different MTU sizes, we have to take care of it. Otherwise, if the MTU size is too large, then it would not be possible to transport it over a subnetwork with a smaller MTU. Okay, so here's a summary of other protocols using TCP, UDP. So we have HTTP for web browsing, we have FTP for file transfer, SMTP used for email, probably now, rather IMAPs used, I would assume, but anyway, SSH, for remote login, probably most of you know. Telnet, I'm not sure whether it's still used, but it used to be the state-of-the-art tool for a remote terminal access. And then based on UDP, we have DNS, so domain name resolution. So that's the question is, how do you learn which IP address you have to connect to? And for this, DNS is used. Yeah? So if you enter, for instance, in your web browser, kit.edu, then this URL is first sent to a DNS server, and then this DNS server will tell you what the actual IP address of this URL is. SNMP for network management, an extremely important protocol, still used now, like for printer management, router management, and so forth. But I think only few people know about this protocol, I would say. Yeah, RTP for streaming, trivial file transfer, so TFTP, much faster than pure FTP, and NFS, which is there for remote file access. Okay. Now, how all of this now apply to a mobile network? And before continuing, a bit of terminology once again. So we have here our mobile network where we start with our terminals, yeah, which are typically called UE in our mobile network, and which have usually a data connection and a control connection. Yeah? We are now rather talking about the data connection in the following, yeah? So only about this connection and not the control. Then we have here our radio access network, which basically includes our base stations and the transport network. Okay. Then we have here our core network. And finally, we have here our data network, mainly the internet. Yeah? So when you, for instance, want to access a website, and it's in the data network. Now assume we have here a terminal that wants to access a website, and the website provides data. Then what happens is the UPF would receive here for instance, a TCP IP packet, yeah, and the UPF, so the user, so this one here is the user plane function in 5G, and in LTE it has been the packet gateway. The UPF would see, is there any active connection? Okay, once again, my battery of my pen is low. Okay. The UPF would see the IP address and know, okay, the IP address belongs to a certain user terminal down here. Okay, now I'm a bit screwed up. Okay. Here to this user terminal, and then it would know, okay, it belongs to a certain base station where this UE is connected. And between this base station and the UPF, we have a so-called tunnel. Yeah, so that's kind of a pipe where you can put in the data, and you will know, okay, this data will be delivered then to the base station. And this tunnel is maintained with this GTP, so GPRS tunneling protocol. So here, that's our tunnel. And the UPF would now just put your IP packet into this tunnel. It would go down all these different this protocol stack. Within the transport network, we have some routing in order to get to the destination and eventually go to our base station. Yeah. So that's the way how your IP packet, yeah, when you for instance accessing a website, would actually reach the base station where your mobile terminal is connected. Okay. And all of this, yeah, so this protocol stack, that's then the protocol stack within the core network. So basically GDP over UDP. Now at the base station, the IP packet comes out of the tunnel, and the base station itself is not looking into your IP packet. Yeah, so because the base station will read the header of your GDP. So you have here your GDP connection, right? And okay, so and in the header of the GDP packet, so based on this information, based on this information, the base station will know to which user terminal the data has to be delivered. Okay. And then all of this data is put in the so-called SDAP, so down here, and then goes through all the different RAN protocol stacks. So the packet data convergence protocol, the rate link control, MAC physical layer. Then it goes over the air, it goes in the terminal through the processing. Yeah, so it goes down here, over here. This is now that's really the air interface here. And then it pops out at the user terminal. And this is now called the RAN protocol stack. And just to repeat from what I said at the very beginning of this lecture, on each of these layers, you have an own logical connection. Yeah, so you have an own PDCP connection between the base station and the user terminal, same on RLC and the same on MAC, which is important, for instance, for to ensure sequence, so that the packets are provided in order, provided reliably, and so forth. Okay, and only at this point now your IP packet will again be visible for the user terminal. And this is quite important because for the user terminal itself, it's just an IP connection. Yeah? So if you have your WhatsApp, for instance, or your web browser, so on your mobile phone, the application itself will not know whether or should or doesn't need to know whether you're connected through a Wi-Fi connection or a mobile communication connection. Yeah, because you just get an IP packet, and whatever happens below, yeah, on layer 2 and layer 1 is irrelevant for the application above. Yeah, you can retrieve this information. So sometimes it's quite important to have it, for instance, to avoid large file downloads over a mobile network. But it's something that that your operating system has to ask for actively, yeah, from the underlying protocol stack. Okay, and then yeah, IP packet is delivered, the TCP port is determined, and then eventually it's then provided to the HTTP process on your mobile phone, naming your web browser. Now again, because that's very important, so you have here one logical end-to-end TCP connection, yeah, between your mobile phone and the browser, and that's important because it's stateful. And only because of the stateful TCP connection, the web server actually knows where to deliver the website, yeah, to which terminal. Because this UPF here also performs NAT, yeah, and then the IP address that you have here on your mobile phone is actually a private IP address, and here you have an public IP address. And if your mobile phone sends a request for a website, it establishes an IP connection to your UPF. The UPF translates your IP address, asks the web server, you get a response, and then your UPF would actually translate it back to a private IP address in order to deliver it to your mobile phone. Okay, now from the outside world, the only thing that is actually visible is a router. Yeah, so a mobile network actually acts like a router plus firewall, basically. A problem or a challenge that we currently see is in industrial networks, where you would not connect devices on IP layer, but rather on Ethernet layer. Yeah, so using Ethernet. MAC addresses, so a flat layer 2 network. And here you would have to implement the same processes as in a fixed line network. Yeah? So you have to perform your ARP, yeah, to maintain also a forwarding table at the UPF in order to know where a certain MAC address has to be forwarded, or in which tunnel basically a certain MAC frame then has to be forwarded. And this actually also shows nicely the flexibility and the ability to adapt by a 5G network, because the underlying technology, so your radio access technology and core network technology, is exactly the same. Yeah, you use the same base stations, you use the same core network functions, but you can easily then also deliver an end-to-end layer 2 connectivity, which makes 5G much more flexible in this case, and also applicable to industrial networks. From the outside world, in this case, a mobile network would only look like a switch, basically, because you just forward the frames on layer 2. And this is quite important, because then for the user of your 5G network, you don't have to care about how base stations are configured and so forth, because you would only care about that there is a bridge, so which is underneath a mobile network, and then you would up here have some network management system, so NMS, which is then typically using here SMTP in order to retrieve then information from your mobile network and the other bridges. Excuse me. Okay, so this was already the last slide. Just to summarize this again, so you should now have a good understanding of the very basic operation principles of internet protocols, like, so what's the OSI reference model? What are the different network layers, so physical layer, data link layer, network layer? Why do we need then these logical layers, so transport layer and application layer? How is this mapped to actually internet protocols like Ethernet, IP, TCP, UDP, and so forth? And how these internet protocols are used within a mobile network. And I think if you understood this very basic principles, then you're also very well prepared for the mobile communication lectures, which are then more focusing on the operation of a radio access network, and in particular later then also of the core network. Okay, then thanks for listening. And if you do have any questions on this lecture, you're always welcome to send us an email or use the forum on Ilias. Okay.